Dear students, here we will explain the Newton's second law of the motion applied to the uniform circular motion. That is, here we will explain the application of the Newton's second law of motion to the uniform circular motion. So first we need to explain the uniform circular motion. What is the uniform circular motion? And uniform circular motion is that motion in which we consider body or particle is moving in a circular path. Okay, body is moving in a circular path with constant speed. Okay, body moving in a circular path with constant speed, then it is called as uniform circular motion. So speed should be the constant. Okay. And then any body which is moving in a circular path with constant speed it experience an acceleration which is called as centripetal acceleration. Centripetal acceleration, and the acceleration of this magnitude can be represented by AC, and this magnitude is equal to V square over R. So V is the speed and R is the radius of that circular path. So here a centripetal acceleration is always directed towards the center of the circle. It always towards the center of the circle. And secondly, this acceleration is always perpendicular to the velocity. Okay, perpendicular to the velocity vector. So if this centripetal acceleration has any component that is parallel to the speed, parallel to the velocity, then the speed of the object will not be the constant. It will not be the uniform motion. So for the uniform motion, the acceleration should always be directed towards the center of circle. And so this is called as uniform circular motion. So we can visualize the uniform circular motion. So here you can see that the body which is attached, animals attached with the string, and it's moving in a circular path. And here you can see that acceleration, centripetal acceleration is always directed towards the center of the circle, and this one is the radius of the circle. So it is moving in a circular path. So we can explain this uniform circular motion, and um, here you can see that any point on the circle during at any instant of time, its acceleration is always directed toward the center of circle, and velocity vector at all points are perpendicular to this acceleration. So velocity vector is always perpendicular to the acceleration, and acceleration is directed toward the center of circle. So it is moving with the constant speed in a circular path. So the question here is that why does ball move in a circle? Why does ball move in a circle? Okay, so we can answer this question, and but first we need to know that there is also inertia. So here in any body which has the mass, which has the inertia. So here the inertia of the ball is its tendency which try to move the ball in a straight line. Okay, inertia of the ball try to move the ball in a straight line. Now which thing compel the ball to move in a circle, although the inertia of the ball try to move it in a straight line. So the answer to this question is that this is the string force. String force are the force of string to which this ball is tied, and the force exerted by this string. This force compel the ball or move the ball in a circular path. So the force exerted by the string is always directed toward the center of circle. So the string force is always directed towards the center of the circle. Okay, it is directed toward the center of the circle. So this force, string force, prevents the ball to move in a straight line and tend it to move in a circular path. So as this force of the string is directed toward the center of the circle, that's why this force of string is called as centripetal force. Called as centripetal force, and it can be represented by Fc. Here the subscript C represents the centripetal force, and at any point on the circle it will be directed towards the center of the circle. So this force always acts towards the center of this circular path, and this force always causes the change in the direction of velocity. This is the cause of change in direction of velocity vector. Okay, velocity of, as we know that when body is moving in a circular path, then the velocity vector is always changing its direction at every instant of time. So this centripetal force which causes the velocity vector to change its direction at every instant of the time. So if we stop applying this force, then where this ball will go? So this ball will move tangent to the path, tangent to the circular path. It will move in a straight line. So when the string break at any point, then the ball move in a straight line. So it can move tangent to the circular path. So here we can apply the Newton's second law of motion. By the Newton's second law of motion, we can find the value of net force which causing the centripetal acceleration. So, according to the Newton's second law of motion, net force is equal to ma. Here, the acceleration is the centripetal acceleration, so it will be equal to mv square divided by r. So again, I can write it like that. So this force is the force of string, which is responsible, or we can say that this is the tension in the string, or the string force which is responsible for the ball to move in a circular path. So this tension in the string provides the centripetal force to the ball. Okay. Now we comes into another quick question, and here, is it possible for a car to move in a circular path in such a way that it has the tangential acceleration but no centripetal acceleration? Is it possible for a car to move in a circular path without having the centripetal acceleration? So the answer to this question is no. No, it is not possible for a car to move in a circular path without having the centripetal acceleration or radial component of the acceleration, or having only the tangential acceleration. So the tangential component of acceleration is active. It is act only when the body is moving in one dimension or in a straight line. So when body is moving in a straight line, then in that case, the centripetal acceleration or radial component of acceleration is equal to 0. So for the car to move in a circular path, the radial component of acceleration or centripetal acceleration should not be equal to 0. So centripetal acceleration is necessary for the car to move in a circular path. Without centripetal acceleration, car cannot move in a circular path. Now we have some other question here. The question is that forces that force we know that causes the body to move in a circular path is called as centripetal force. This is the centripetal force which causes the bodies to move in a circular path. So uh, here it produces the acceleration which is called as centripetal acceleration. The acceleration produced by the centripetal force is called as centripetal acceleration. And in nature, we have the variety of the forces, like we have the normal force, um, we have like the normal force, and there are the force of friction, or there can be the force of tension. So there are the lot of forces which exist in the nature. So here the question is that can we add the centripetal force to the list of naturally existing forces? Is it possible to consider the centripetal force as a new kind of the force? The answer to this question is that no, we cannot add centripetal force to the list of existing forces because the centripetal force is not a new kind of force. Not a new kind of force. Why we cannot consider it as a new kind of force? Because it is the force, not a new kind of force, but rather it is the role of existing forces to move the body in a circular path. So any force of existing forces in the list of existing forces, any force can play the role of centripetal force. So it's not a new kind of force, rather it is the role of existing forces to move the object in a circular path. Let's suppose here you can see here in this figure, Earth is moving around always in a circle around about in a circular path around the sun, and so here this is the gravitational force. Here this one is the gravitational force which is responsible for the circular motion of Earth around the sun. So here the gravitational force is responsible for the centripetal force which is provided to the earth to move in a circle. So here centripetal force is not new kind of force. Rather, gravitational force is playing the role of centripetal. Gravitational force providing the centripetal force to the earth to move in a circular path. Let's we go to another example. So here you can see this is another example. This is the turntable. This one is the turntable. Suppose that any object which is sitting on the turntable, and so here, if any object is sitting on this rotating turntable, then centripetal force in this case will be provided by the force of friction. So here, in this case, the force of friction between this object and turntable is responsible for this object to move in a circular path on rotating turntable. So again, here the force of friction is not a new kind of force. Rather, the force of centripetal force is not a new kind of force. Rather, the force of friction is playing the role of centripetal force. This force is providing the centripetal force to this object to move in a circular path while on the rotating turntable. And let's suppose here this one is another figure. In this figure, you can see that when the boy which is holding the string, and on the other end of the string we have the rock or any body of mass m is attached, and he is moving this rock on a circular path. So as it is moving in a circular path, it means that here is the centripetal force which keeping this rock or body to move in a circle. Okay, and move in a circle. So here the centripetal force is provided by the tension in the string. Tension of string. So tension of the string is providing the centripetal force to this rock to move in a circle. So from all these examples, we can say that the centripetal force is not a new kind of force. It's not new kind of force. Rather, it's the role of existing forces. Okay, we can say that, or rather, the role of existing forces to move the body in a circle. Move the body in a circle. So that's why we cannot add the centripetal force in the list of naturally existing forces. So this is an example. Here we have already discussed that ball of mass m is which is attached with the string and it's moving in a circular path. And let's suppose the mass of the ball is equal to 0.500 kg or kilogram, and the length of cord or string is equal to 1.50 meter. Here the length of the cord is equal to the radius of this circular path, and it's equal to 1.50 meter. And if the cord withstands with the maximum tension, so the tension of the cord or string, tension of cord or string, so this one is equal to the 50 Newton. So here you need to calculate the maximum speed of the ball. So here we will calculate the maximum speed of ball before the cord can break. Okay, so now we can go to the solution. We know that the force that causes the centripetal acceleration here in this case is the tension in the string. So here we can apply the Newton's second law, sum of forces equal to ma, and so here the force of the string is the force which provides the centripetal acceleration. A is equal to mv square r. So the speed will be equal to PR divided by M. Okay, from here you can see that V is directly proportional to the tension in the string and V is inversely proportional to the mass of the string. So we can say that larger mass requires a large tension. Larger mass requires a large tension. And small mass requires the small tension. Small mass requires a small tension. Okay, so when here we can calculate the maximum speed of the ball. So the maximum speed of the ball, it will be equal to T maximum into R divided by M. So when we put the value, tension in the string is the 50 Newton into radius R, length of the cord is 1.50 meter, and divided by mass of the ball is 0.500 kg under root. So the maximum speed of this ball before breaking point, after calculation, it comes to be the 12.2 meter per second. So this is the speed, maximum speed which is required by the ball before breaking or without breaking to move in a circular path. Okay, so now we comes to another problem, and this is an example of conical pendulum. This is called as conical pendulum. So here you can see that the body of mass m or ball is suspended from the string of length L, and so it's moving in a circular path over the horizontal circle, as you know that strings sweep out on a surface of cone. So that's why it is called as conical pendulum, because the ball sweep out the surface of cone, sweep out the surface of cone, or it make a cone while moving in a circular path. Here you can see that it's making the cone. So that's why it is called as conical pendulum. Here I can make the geometry. So this one is the string, and string, at the end of string there is the length of cord L and the mass of ball. So we can draw, this is normal. So this ball of mass m, it suspend a circular path. It's moved in a circular path. So this one is the angle theta. Now this is the center of the circle, and this one is the radius vector. Okay, this one is the radius, this one is the radius, this one is the radius vector. So again I can split the different tension vectors. So here this one is the length, and tension T is the here the tension of this cord. This tension of the cord, tension force, is responsible for this conical pendulum to suspend a circular, to move in a circular. So here we can uh, divide it into the component. So this is the tension in the string, and it's making an angle theta. So this component is called as the T cos theta, and this component is called as T sin theta. So from here you can see that this component of T sin theta, and this one is the T cos of theta, and downward is the force of gravity mg. So here the you can see that as the force is centripetal force is provided by the tension, and it is the T sin theta component of the tension which provide the centripetal force, because this component is directed towards the center of the circle. So this T sin theta is responsible for this ball to move in a circular path. So we can here make the two equations. The first equation is T cos theta component is balanced by its weight mg. So this is equation number 1. And secondly, we can say that by applying the Newton's second law of motion, when we apply Newton's second law, so according to Newton's second law, the force is sum of the forces equal to ma. Body is moving in a circular path, so it is equal to mg square. So here the force is the T sin theta component. So T sin theta is responsible for the centripetal force uh, equal to mv squared divided by r. So this is the equation. Okay. Now dividing the equation 2 by equation 1. When we divide and we solve, we get tan theta, tan theta is equal to v square divided by rg, or v will be equal to rg into tan theta under root. Okay, so but when we solve the geometry, and according to geometry, if this is the length of this string and here this one is the angle theta, and so this is the L sine theta and this one is the L cos theta. So L sine theta is the radius, is along the radius vector, so R will be equal to L sine theta. So putting the value of R is equal to L sine theta, V will be equal to L G sine theta into tan theta under root. So this is the maximum speed of the ball, which is in the form of conical pendulum, and here you can see that it is independent of mass. It is independent of mass, and this depends on the value of g, on length of the cord, and sine theta and tan theta. Thanks for watching. For more videos, please subscribe our channel.